Okay, hello. Hi there. Time for another video here, another physics video. Uh, Today we're going to take our discussion of kinematics just a little bit further than we did last time. I'm going to start off at the same place though. Just the idea of things I'd like you to come away understanding after this is all over, your physics year is all over. If we know a few things and we know the patterns involved, we can figure out a lot more information. And that's with things besides physics too. If we know the patterns, we have a little bit of information, we might be able to see where we're going. Good with predicting future events. Okay, so how has this been helpful for society? That's a good question to be asking. And what can we gain by understanding this? And how are the units important? In your paper there, I'm also adding a question here, a couple of questions that I think are kind of interesting. So again, how has this helped society? I'm telling you it has. Well, how has it? That's a good question. And also, why didn't people know this before the 17th century? I mean, it really started with Galileo in a big way in about the 17th century. We started defining these things. Why did it take people so long? It's an interesting question to ask. And with your Cornell notes, you should be asking higher level questions, of course. Okay, so today what we're talking about is acceleration, and I'm wondering, in your words, what is acceleration? What does that mean to you, acceleration? Okay, you probably have an idea. You step on the accelerator, maybe picking up speed if you hit the gas pedal, or the accelerator they call it sometimes. But the physics definition is that acceleration is the rate of change for speed. How fast is speed changing? That's acceleration. So we're doing things symbolically, of course, and then we're going to start with this idea of acceleration. Acceleration is the triangle here is the Greek letter delta, and it's a shorthand way, a symbolic way of saying a change in something. So delta V over here in this equation means the change in speed, and that's divided by the change in time. How fast is speed changing? How much time did it take? That's the idea of acceleration. All right, so let's see how this works out in an equation like we've done before. Up until now we've talked about a constant speed or an average speed, right? So there was only one speed to be talking about. But now we're going to start talking about the idea of a speed that an object has before and after something is going on. So we have to add a little bit of a subtitle or subtext to a subscript to our symbol for speed. I'll show you what I mean. So the first thing that we're going to do is we're going to identify the information. So here's the subscript I to say the initial speed is 0. It starts at rest, right? So the initial speed is 0 meters per second. And there I'm telling you, VI is the initial speed. And we're going to use VF for the final speed, and here, after 10 seconds, it had a speed of 50 meters per second. So, in these acceleration problems, we have to distinguish between the two speeds. VF is the final speed. All right, the time is 10 seconds, and here is my equation that I was showing before. A change in anything is your final value minus your initial value, right? So the final speed minus the initial speed is the top of the fraction, and the time is going to go on the bottom. So that's what we have here. Now we usually start our time at 0 seconds, so the change in time is just this t, this 10 seconds. Okay, so when we plug it in, there's my 50 meters per second minus my 0 divided by 10, and that means that 5 is the answer. Remember again, you are always going to identify your information, and then you're going to show your work. Now in the showing the work, that's underneath this solid line here, is showing the work. You don't have to put the units in there. I'm putting them in there just to be as clear as I possibly can. But 50 minus 0 is 50, 50 divided by 10 is 5. And how about the unit? What is the unit for acceleration? 5 what? Well, if you divided meters per second by second, you would come out with meters per second squared, and that's the unit for acceleration. Now you might have questions on how I got that. So if you do, make a notation in your notes and bring it to class. We'll talk about it. Okay, so 5 meters per second squared is the acceleration. Okay, so if we rearrange this formula, remember we did that with our first kinematic equation, we'll end up with our second kinematic equation. So if we solve for VF here, we're going to end up with this. Now that's a good one to see if you can do. Can you do that? And if you can't, ask me maybe in class, how did you do that? And I'll be glad to tell you, of course, and then you'll have a deeper understanding of what we're doing here. Not a bad thing. Okay, so this is going to be right here, this VF is equal to VI plus A times T. That is the symbolic representation for the second kinematic equation. Okay, so let's try it here. Let's try one. Here's a problem for you. Why don't you give this a try, and when you come back, I'll show you my answer, and after you hit the pause button, and we'll talk later. Okay, welcome back. Well, here's my solution. Let's see how you did. First of all, we're identifying the information. So what do we know so far? And I'm putting in one more piece of information. What is the thing that we're looking for? So here is the first step, symbolically representing the givens, the information. Here is the solution for the problem. And once again, I'm throwing all my units in there, maybe to show you how things are going to be canceling out, which you can certainly ask about. You don't have to do that in your problems. You've already shown the units in your givens. But at any rate, here we have 0 plus 12 times 5. So 12 times 5 is 60, and 0 plus 60 is 60 also. So the final speed is 60 meters per second. And again, if you have any questions, because this stuff can be confusing, it's very confusing, can be anyway. Please ask about it in class. I can certainly help you when we're back together. Okay, so how about this? How far did the object travel during that time period, right? You might be tempted if you're thinking about this. Well, what are you thinking? What are you thinking? How far did it travel? You got the final speed of 60 meters per second. It took 10 seconds. How far did it travel? Well, it's not as easy as that. D is equal to V times T, but first we have to find the average speed. Obviously, if it started off at 0 and ended up at 60, 60 is not the average speed. 60 is just the final speed. But the average of two numbers is the two numbers added together divided by 2. So the average speed here is 30 meters per second. And if we're looking for distance, distance is speed, 30 meters per second, multiplied by 5 seconds. I'm sorry, 5 seconds, not 10 seconds. I think I said 10 seconds a little bit earlier. Well, 150 meters is the answer, because the average speed is 30 meters per second. Okay, and again, this only works if the acceleration was constant all the way through, but for our problems, they pretty much will be. All right, that is it for this slideshow. So I hope you enjoyed it, and I look forward to seeing you back in class. Thanks for watching.